But before we get into the detail of how sodium and chlorine are actually forming this ionic compound together, let's look at a few more characteristics of ionic bonds that are present in ionic compounds. So within an ionic compound, you don't just have a single negative ion and a single positive ion. Because there's going to be lots of other ions there as well, you're going to actually have attraction between more than one positive and negative ion. And this actually allows them to form ordered arrays, such as what you see here on the right hand side. So if you look at the negative chlorine in this case, which is forming the chloride ion, then it's attracted to quite a few different positive sodium ions. So this allows them to stack together and form these ordered structures, which can actually form a crystalline-like lattice. So this is why when you have, for example, table salt, which is NaCl, it forms that crystalline sort of beady-like structure. So we have that attraction between the positive charged ion and the negative charged ion, which is basically holding together the whole structure. So the ratio will be such that overall the whole structure itself will have an overall neutral charge. So the number of positives has to equal the number of negatives. So to name an ionic compound, basically you're just naming the two ions involved. So for example, if it was magnesium and sulfur, then it would become magnesium sulfide. If it's calcium and chloride, if it's calcium and chlorine, it becomes calcium chloride. So the second one has IDE at the end of the name, just to show that it's part of an ionic compound. So a little bit more background information about one of the most common ionic compounds, which is NaCl, also known as table salt. So salt was actually so expensive in the Middle Ages that it was commonly referred to as white gold. So it was that valuable that it got this nickname here. An interesting thing about salt and why a lot of people like to use it in their cooking is it actually will open up some of the taste receptors in your tongue, enhancing sweet and sour flavors while suppressing bitterness. So in general, a lot of people would think adding salt to a meal can improve it, and there is actually scientific evidence behind why this is. And interestingly, the body having too much or too little salt is actually going to be fatal. We do actually require normalized levels of sodium and chloride ions from the NaCl here to actually allow the body to be able to function as it needs to. It also plays an important role in blood pressure. So a very high salt diet can actually have a role in increasing blood pressure. So as you learn about in BioH, there's sodium and chloride channels in the cell, which can actually allow these ions to move in and out of the cell. And you'll learn more about that in BioH, your BioH subject. All right, so let's now look in detail at how sodium and chlorine atoms come together to form an ionic bond within the ionic compound. So you can see here for sodium, it contains 11 electrons and 11 protons, whereas the chlorine atom contains 17 electrons and 17 protons. So as the metals do, they're going to donate one or more electrons to the non-metal. So sodium needs to get rid of one electron to become more stable, and chlorine needs to accept one electron to become more stable. So we have sodium donating an electron to the chlorine. So this has an effect on the numbers of electrons and the ratio to the protons for both the sodium and the chlorine. So through this process, we see that the sodium atom has become the sodium ion by losing that negative charge from that one electron. And we can see what the consequence of that is. Now the sodium atom, it's actually a sodium ion now, has 10 electrons, which are negatively charged. Still has the same number of protons though, so it's got 11 positive charges. So if we add those together, that corresponds to a 1+ charge, which is why we show Na plus like this, because overall it has one more positive than it has negative. What about for the chlorine? Well, it turns into the chloride ion by gaining that negative electron from the sodium. So let's have a look at its number of electrons and protons now. So instead of having 17 electrons, now it's got 18. So if we do what we did above, so we've got plus 17, and if we take away 18 from that, that corresponds to an overall charge of 1 minus, which is why we have a negative symbol here. So we don't write the 1 in. If it's just 1, we presume, if we don't show a number, it's just presumed to be 1. For example, magnesium, which actually forms a 2 plus ion, will actually have 2 more protons than it has electrons because it's given away 2 of its electrons. So this just shows you how the number of subatomic particles actually shifts between the beginning where they're in the atom forms and after they become the ions. So remember, they're no longer atoms anymore because they have different numbers of electrons and protons, which gives them an overall charge, which is a characteristic of an ion and not an atom. So once we've got the Na plus and the Cl minus, then we get an ionic bond forming together to hold those together, which is the beginning of a ionic compound. So remember, we're going to have not just 2 ions, there'll be lots of other ions as well, which are going to be part of a larger array of sodium and chlorine atoms, which come together to form an ionic compound. So just like an atom, the overall charge of an ionic compound has to be neutral. Basically, this means that the positive charges of the ions has to equal the negative charges of the ions. So let's have a look at an example here where calcium and chlorine are going to come together to attempt to form an ionic compound. So if we look at the periodic table, we can see that chlorine is in group 7, so it needs to form 1 extra covalent bond or gain 1 extra electron by accepting it. So because we're doing ionic bonding now, we're going to have the chlorine atom accepting an electron to become Cl minus. In comparison, calcium is actually in group 2 of the periodic table, so it actually wants to remove 2 electrons to become positive. So in its ion form, calcium is now 2 plus and the chloride ion has a 1 minus charge. So let's have a look what will happen if we have 1 calcium and 1 chlorine atom trying to form an ionic compound. So here we can see the charges. The calcium has a 2 plus charge and the chlorine has a 1 minus charge. So if we had a compound such as this, then the compound would be CaCl. However, this compound actually can't exist. Can anyone see any problem with having a calcium ion attached to a chloride ion in this way? It's because the charges are unbalanced. The calcium is contributing 2 positives and the chlorine is contributing a single negative charge. But remember, for an ionic compound to exist, it has to have an overall charge of 0, a neutral charge. So we need a way to balance the positive charges from the calcium using the chloride ion. The answer is basically to have more chloride ions, because each one will only contribute a 1 minus charge. So because the calcium has 2 plus charge, we then need to have 2 minus charges from the chloride ion to counter those 2 positive charges. And because the chloride is only a 1 minus ion, basically the only way you can get 2 minuses is just to have 2 of them. So it corresponds to the calcium, which will be 2 plus, that will actually attach to 2 separate chloride ions, each one having a negative charge there. So if you add up the charges, 2 negatives from the 2 chlorines and then 2 positives from the calcium ion there. So overall the charge is 0. So that satisfies the need for charge being balanced, and we get a compound forming here, which is an ionic compound, which we would call calcium chloride, and the 2 after the chlorine designates that there has to be 2 of those chloride ions there. So because the charges are balanced now, we've created an ionic compound that would actually exist, in comparison to this previous one that would never actually exist because the charges aren't balanced. So for all of our ionic compounds, you always have to have balanced charges. So this may mean that you have more of one atom type, or more of one ion type rather, than the other. So for example, in that first one we looked at, when we had our sodium atom interacting with oxygen, the oxygen actually formed a 2- charge and the sodium formed a 1+ charge. So we actually needed to have 2 sodiums to allow the charges to be balanced, and those 2 sodiums were attracted to the oxygen ion there. It also makes sense in terms of if you're looking at the electron movement, because to become the oxygen that is O2-, the ion in that case, the oxygen actually has to accept 2 different electrons, one from one sodium and one from the other. So if it was only reacting with one sodium, it wouldn't become 2- and it wouldn't be stable. So not only do we have to consider balancing charge, but also the number of electrons each ion actually needs to be stable. So there is a variation of an ion called a polyatomic ion. So a polyatomic ion is basically a group of nonmetal atoms that are connected together via covalent bonds. So it's quite different to what we've seen in our ionic compounds, where we've got one metal and one nonmetal atom together. Here in a polyatomic ion, we've got only nonmetal atoms that have these covalent electron sharing relationships between them. The thing about a polyatomic ion is it has a charge. Okay? So we're not going to go into exactly why these carry a charge, but essentially it's because they have more or less electrons than you would expect if there was no charge. So where there's a negative charge, it means they have more electrons. Where there's a positive charge, it means they have less electrons. So you can see from this table here of common polyatomic ions that almost all of them are negatively charged polyatomic ions. There's only one exception to this, and that is the ammonium ion, NH4+. So this is actually produced as part of amino acid metabolism that we'll look at in our metabolism section of the course. Other common polyatomic ions that we'll see quite a lot in the course include the hydroxide ion, the carbonate ion, which is involved in acids and bases, and also phosphate, which is heavily involved in metabolism. So those are probably the main ones that I want you to be aware of. Don't get too hung up on these polyatomic ions. The larger focus for this section was the ionic bonding and understanding how atoms become ions and then how the charges are balanced to satisfy the need for an overall charge of 0 and also to make the atom stable. So the last thing we're going to have a look at now is comparing the 2 types of bonding that we looked at in this session. So earlier in the session we were introducing covalent bonding, and more recently we've been looking at ionic. So there are key differences between these 2 types of bonding. Remember that the majority of what we'll see coming up in the course will be to do with our covalent bonding, but we will refer to ionic bonding from time to time as well. So some of the key characteristics of covalent bonding is that it occurs between 2 non-metal atoms. So you'll never have a metal atom within a covalent bond. The other thing about covalent bonding is it relies on electron sharing between the 2 atoms involved in the covalent bond. And the end result of the covalent bonding is that all of the atoms involved in the covalent bonding will form a covalent compound. And by doing this, each atom will obtain a full valence electron shell to become stable. So in the case of our water molecule here, the oxygen and the two hydrogens that are part of the covalent compound are all stable because they all have full valence electron shells. Another key thing with covalent bonding is the atoms, there's atoms before the atoms attach together, and they remain as atoms once they're within the compound. So let's compare this to ionic bonding. So ionic bonding will occur between one metal and one non-metal atom. So it's never going to involve two metal atoms together, and it will never involve two non-metal atoms. So it has to be one metal and one non-metal. So in ionic bonding, the metal atom will lose an electron, which is accepted by a non-metal atom. And this causes both atoms to actually become ions. So the metal atom that loses an electron will become a positive ion, whereas the non-metal atom that accepts the electron will become a negative ion. So you can see that in the example down here, that the participating atoms in the ionic bond turn from atoms into ions, and this allows them to have full valence electron shells to become stable. So the example we have here is sodium chloride, which is where the sodium ion, which is a metal, becomes positively charged, and the chloride ion, which is a non-metal, becomes negatively charged. So we've reached the chance for you guys to have a go at another one of these participation plus questions. So there's a lot to get your head around in this session, so I do really encourage you to have a go at these conceptual type questions to check your understanding. And we've also got these revision questions now. So have a go at these revision questions 7 to 10 on your LMS revision quiz to confirm your understanding of what you've seen in part 3 here. So to summarize what we've learnt in part 3 of this session, we had a look at ion formation. There's two ways this could happen. An atom could lose electrons, and that was causing it to become a positive ion that we call a cation. So this happens to metals like sodium that lose an electron to become a positively charged ion. The other way an atom can form an ion is to become a negative ion by gaining electrons. Remember, the electron has a negative charge, so by gaining an electron, you're becoming more negative and hence forming a negative ion. So chlorine can gain an electron to become the Cl- ion. So chlorine is a non-metal. Ionic bonding basically involves one metal and one non-metal. So the metal is going to be the donor of the electron, which is going to be accepted by the non-metal, which causes each to become an ion. So we've got the positively charged metal cation and the negatively charged non-metal anion coming together to form the ionic compound. And remember, to be a true ionic compound, it has to have an equal number of positive and negative charges as well. We also saw there's another group that can have a charge, which are polyatomic ions made up of non-metal atoms that are connected via covalent bonds, normally carrying a negative charge. These polyatomic ions are normally having that negative charge there. And we also saw the comparison between the two types of bonding we covered in this session. So covalent bonding is an electron sharing relationship between two different atoms, and we've got two electrons being shared in each covalent bond, and those two atoms involved are always non-metal atoms. Whereas ionic bonding occurs between one metal and one non-metal atom, and this is where the metal atom will lose an electron, which is accepted by the non-metal. So hopefully you can see how we've built on some of our understanding of the atom structure from the first session. So we're going to build on what we did today, looking at covalent bonding in a lot of different sessions throughout the entire unit. So make sure you do some revision to make sure you have your head around all the concepts we looked at today. It really is the foundation to a lot of other things that we're going to do in this course. So good luck with your revision, and I'll see you for our next session.